We now turn to electron beam lithography. E-beam lithography parallels optical lithography, except the source of radiation that damages or strengthens the resist is an electron beam rather than a beam of light. The second difference is that because the beam is generated in a device just like a scanning electron microscope, the beam can be turned on and off by a computer as it's scanned over the surface, and this therefore means there is no necessity for making an optical mask, which is one of the long time and expensive processes in photolithography. So it's a great technique for rapid processing or prototyping of nanostructures. It works just like optical lithography, except now here's the surface and here is a polymer resist, and as the beam is scanned over the surface, focused down to a sharp point, it may be turned off at certain places and then back on again, so as then to lead to a feature in the resist that is unexposed. In this case, here I've shown a negative resist. So this, of course, can be done digitally, and it means that the generation of new patterns is extremely trivial. In principle, the resolution is very high, but not as high as one might think, given that the source is an electron beam. This panel shows a process in some detail for, in this case, under A, deposition of metal. And so you see here first the exposure of the resist to the electron beam. This is a positive resist, so that when the resist is developed, holes are left behind. In this case, metal is evaporated onto the surface, and then the polymer support dissolved away to leave the metallization on the surface. Here's an example of a structure built by a process just like that. It's a series of metal rings on a silicon support for acting as a Fresnel lens for focusing X-rays. This scale bar here is 1 micron, so you can see the features are considerably smaller than 1 micron. The example in panel C is a single electron transistor, a device that we will talk about in Chapter 7. Now, why would E-beam lithography not give you features of almost arbitrary smallness given the resolution of the electron microscope, as we talked about it in Chapter 4? The reason is, of course, that here the electrons have to do work, they have to interact with the resist, and they scatter from the resist and the underlying silicon. These two panels show you calculations of the electrons scattering for focused beams of 10 kilovolts and 20 kilovolts. The scale bar at the top is in microns, so you can see that even for the lower energy beam, the width of the damage done to the polymer, or the strengthening, depending on whether it's a positive or negative resist, is a significant fraction of a micron. And you can see that the beam profile changes quite drastically at 20 kilovolts now, with an interaction over many microns, although the tail of the beam inside the polymer is somewhat sharper. So what this means is it's hard to get resolutions with electron beam lithography that are really much smaller than a few tens of nanometers, although with a great deal of care and expertise, features as small as 2 nanometers have been made by E-beam lithography. Let's turn now to micro-electromechanical structures, MEMS. These came about when it was realized that one could make mechanical components by undercutting structures on the surfaces of silicon wafers. We'll talk about some diverse examples of this in the rest of the book, but let me focus now on the obvious one from Chapter 4. How does one make those atomic force microscope probes? Here's an example of how to make AFM tips very sharp, and in this particular paper, the process that was developed was one to make the tips not only sharp, but also of a high aspect ratio, so that features with very high topography could be imaged. So originally, a piece of silicon oxidized, and it was masked out by this mask that you see on top here, and then etched away by reactive ion etching, so that now one has the mask the silicon and the oxide etched away like this, and then the whole thing covered with a layer of oxide again like this. In order to get the high aspect ratio device, so I'll draw this as it is now on a flat surface, a polymer coating was put on by a low angle flux of material, which then protected the sides of these pillars, but not the flat surfaces, so that by carrying out one of these anisotropic etches I talked about with potassium hydroxide, this device, by being oriented in the right direction on a crystal plane, could be etched down then as a straight column to produce the structure shown in D. Then finally the tip was sharpened and the mask removed, because the outside of the mask is oxide and the inside is silicon. By etching the oxide away with hydrofluoric acid, this causes the mask to fall away and then leaves behind a sharp silicon point. The next slide illustrates the making of a complete cantilever. In this particular slide, it's done by first of all making a tip structure by techniques that I just showed on the previous slide, and then protecting the region that you wish to become the cantilever by implanting with boron, masking off where you want the cantilever to end. By this means, a reactive ion etch then etches out a pattern in the silicon that leaves the more resistant boron-doped silicon behind. This is then covered with a layer of thermal oxide and silicon nitride to protect the top. The whole thing is then exposed to a KOH etch, which of course can't etch this protected region here. And then finally the silicon nitride and the oxide layer removed to leave a cantilever in which, as you see, the probe here now is really made by molding this original probe on the surface. MEMS structures can be extremely exotic. Here is an example of an optical beam steering mirror. You can see the mirror as a shiny piece of silicon in the middle. It's held by torsion bars, which are very small pieces of silicon attached to this gimbal mount that similarly have torsion bars connecting them to the outer rings. So this thing then is a mirror, those whose pointing can be controlled by bending these rings towards or away from the underlying surface. That's done with these metal contacts here that provide an electric field, so that with a contact to this silicon device here, you can attract it or repel it from the surface so as to bend it as desired, and thereby steer a mirror. There's a picture in the book of a device made of many thousands of these. The device in the book is a high efficiency screen that works by reflecting laser light from the millions of mirrors you see on the surface of the device.